How close is too close for a dangerous supernova? Can we realistically hitch a ride on an interstellar object? Is there radiation coming from dark matter-rich areas? And in Q&A Plus, are there multiple dark matters and dark energies? All this and more in this question show. It's time for the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I'll answer them here. All right, let's get into the questions. Known unknown. Hey, Fraser, can you tell us any information about the interactions between neutrinos and dark matter? So dark matter, of course, is this ongoing mystery about the universe. Why do galaxies rotate too quickly? Why do we see this gravitational lensing of light as it's passing from distant regions of the universe to us? Why do we see sort of concentrations in the cosmic microwave background radiation? There's a bunch of these observations that astronomers have collectively gathered together and called dark matter. And as always, dark matter could be matter. Dark matter could be that we don't understand gravity. Dark matter could be that the models are wrong. Dark matter could be that the observations are incorrect. Like don't get too hung up on the word dark matter. And so when dark matter was first discovered, in 1936 by Fritz Zwicky, astronomers had no idea. Like they said, okay, maybe there's some kind of extra mass and maybe gravity doesn't work the way we think. And there was this hypothetical particle called a neutrino. And since then, neutrinos have been discovered. And neutrinos are very similar to what dark matter would be like. We always talk about how that there are hundreds of billions of neutrinos passing through your body at all times, just coming from the sun. And you don't feel them. They don't interact with your body in any way. It's only when you build a giant detector a kilometer across, in Antarctica or in an ocean, and you put detectors all through this area, you detect the occasional interaction with a neutrino hitting a molecule of water. But it doesn't happen very often when you think about that. And they always say, a neutrino could travel through a light year of lead and not interact with any of the protons in the lead. So neutrinos have mass, probably. They follow the distortions of space-time. So they probably have gravity. And even if they don't have mass, they would have gravity due to the E equals mc squared, right? The energy equivalent for their mass. So if you just had enough neutrinos, then that would be dark matter. And this was a very seriously considered solution to the problem. But the problem is that the characteristics of whatever dark matter is, it has to be moving very slowly. And neutrinos move close to the speed of light. And so they have been ruled out as an explanation for dark matter. You're left with something that has a lot of the same characteristics as neutrinos, but are very slow moving. And so that's why one of the ideas is a thing called a sterile neutrino. But there's other possible particles to explain that sort of missing mass. You detect the gravity, but you don't detect the stuff that is causing the gravity. But earlier this year, astronomers were thinking about, because there is so much dark matter and because neutrinos are everywhere and they're going through everything, would there be some kind of interaction between neutrinos and dark matter? And if so, how would you be able to tell? So in this paper that came out in January, and we reported on this on Universe Today, the idea is that when you have galaxies that are out there in space, they are distorting space-time with their gravity. And you get what's called a shear. When you think about sort of like the refraction of light, when light sort of moves through a medium and it sort of gets bent, right? So you imagine the effect of that gravity is going to cause a sort of shear on the gravitational lensing, on the space-time around it. And you're going to get this distortion of the light that's coming from a more distant region. And so according to the scientists, and I don't fully understand this, that if the neutrinos are interacting with dark matter around a galaxy. A galaxy is much bigger than what we see. We see the stars in the galaxy, but we don't see the giant cloud of dark matter that surrounds it. And the neutrinos are going to be blasting through that, and they're going to be essentially changing the way the gravitational lensing appears at a level that is potentially detectable by the new generation of telescopes that are measuring gravitational lensing. And so in theory, if neutrinos interact with dark matter, then we should be able to detect it in the large gravitational lensing being done by Euclid and Nancy Grace Roman. So stay tuned for that. Just Chris, do we know if there's any more or less radiation in areas that we suspect that have more dark matter? So there doesn't seem to be any indication that there's more or less radiation coming from areas where there is suspected to be dark matter. Like, we know where the dark matter is. You can do gravitational lensing to be able to see the distortions of light around galaxies, and that allows you to map out where the dark matter is. And in this way, astronomers have found entire galaxies that have almost no regular matter in them, just dark matter. You can just see this blob of distorting space where there's just a big blob of dark matter. But there is like a potential indication of an excess in energy, and that's from the center of the Milky Way. So for a long time, astronomers have known that there's an excess of gamma radiation that is coming from the center of the Milky Way. And one explanation is that dark matter is falling down to the center of the Milky Way around the supermassive black hole, concentrating and getting so close to itself that it is annihilating. That you've got particles of dark matter, whatever they are annihilating with each other, and then they are producing this gamma radiation that we are detecting in excess. And this is considered sort of like one of the best lines of evidence that there is some kind of accumulation of dark matter at the center of the Milky Way. However, there have been plenty of other explanations for this excess of gamma radiation. For example, there's a lot of pulsars at the center of the Milky Way. Pulsars have these really powerful magnetic fields around them. Magnetic fields can generate antimatter just spontaneously. And then the antimatter finds matter, produces gamma rays. And so that's another perfectly reasonable explanation. And of course, whenever you've got something extreme, like a supermassive black hole, you can just blame almost anything on that supermassive black hole. So maybe there's some interaction between the black hole and matter around it that is producing gamma radiation that is causing an excess. But people have thought about this. It's time to shout out our new patrons at the $5 level and above. Lionel L., Bronze Monkey, JC Woodard, Austin Moore, Orel, Technophile, Rahul Yadav, Christopher Blair, Bill McCullough, and A Bit of a Bear. Join our community at patreon.com/universe today. Dartman X. If the safe zone for a Type 2 supernova is 50 to 100 light years, what is the safe distance for a Type 1a supernova, a white dwarf supernova? The suggested safe zone for supernova kind of changes over time, and so I've seen plenty of estimates. Typically, it's in the 30 light years away to 200 light years away is the safe zone just for supernovae in general. And the risk, the danger, like if you're really close to a supernova, then you just take this straight up blast of radiation that's going to hit your planet. But once you're farther away, the risk is that the radiation that comes from the supernova strips away the ozone in your atmosphere. And so lets in more radiation and everybody gets more cancer. And that theoretically led to extinction events in the past, although not as bad as whatever were the true great extinction events. Geologists have found evidence of fairly recent supernovae that went off in our vicinity in that kind of, 100-ish light years away range. They found isotopes of iron at the bottom of the ocean. And so one was like 6 million years ago and one was like 11 million years ago. And so clearly the Earth was hit by a supernova that some of the radiation hit the atmosphere, but we also have the actual particles that made it to Earth, which is kind of amazing. Type 1a supernovae are more powerful than your kind of bog standard supernova. And so you want them to be about 50% farther than you want a regular supernova. But again, like I said, the ranges for what's safe and what's dangerous change depending on what is the most recent scientific paper. The ones that are really scary are the gamma ray bursts, because those can reach out and impact your planet from halfway across the galaxy. That you could have one that is 100,000 plus light years away, and it could still strip away the ozone out of the atmosphere of your planet. So the example that I was like is that there was a gamma ray burst that hit the Earth, that it came from another galaxy tens of millions of light years away, and it caused the atmosphere to wobble when the gamma ray burst hit us. So gamma ray bursts are next level. There are no stars that have the potential to go supernova in that dangerous vicinity. There are no stars that are thought to be able to go gamma ray burst with the jets pointed at us, again, within a reasonable vicinity. There was a Wolf-Rayet star that was kind of close, and people were a little concerned because it did seem like the pole was sort of pointing at us, but now we know that it's not. And so right now there are no dangerous looking supernova or gamma ray burst progenitors in our vicinity. Gangster Daddy, do type 1a supernova destroy their companion? So a type 1a supernova is a cataclysmic variable star. We actually covered cataclysmic variables in Astronomy Cast this week, and they're a class of star where you have a white dwarf that is feeding off of a companion star. And when it reaches a certain point, the thing detonates as a supernova. That was an overly simplified version of how you get a type 1a supernova, because there's like a bunch of things that are much more complicated about it. But anyway, so what happens to the partner star? Well, there's a couple of ideas. The one is essentially that's how you get stars that are on escape trajectories out of the Milky Way. That you have this white dwarf and you have this star, and they're orbiting around each other, and the white dwarf is causing this star to move very quickly in a orbit around it, and then the white dwarf disappears. And so now the star is thrown out like a slingshot. And theoretically, that could make it move fast enough to be able to escape the Milky Way. So that's one possible explanation. So when we see these hypervelocity stars, they are the result of their partner exploding as a supernova. Aeroskiff, would it be feasible to hitch a ride on an interstellar object? Is anyone planning for such an event? We get this question quite a bit. So the problem with trying to hitch a ride on an object like a comet or an asteroid or an interstellar object is that in order to land safely on the surface of that object, you have to match the velocity. And once you've matched the velocity, there is no need to hitch a ride. You are going the speed of the thing, because then you just coast. When you look at, say, the planets have been coasting around the sun for 4.5 billion years. And so if you had a spacecraft that wanted to be able to land gently on the surface of an interstellar object, you have to put it on a rocket. The rocket would have to match the velocity of the object. And then you have to land gently on the interstellar object. The hard part is done, right? And so you could also just fly your probe and it would fly right beside the interstellar object, and they would just remain in formation for billions of years because you were able to match its velocity. So unfortunately, there's sort of no reason. There's no savings in trying to get to an interstellar object. The benefit that you get is that the interstellar object is made of stuff. And so if you want more propellant, you want more raw material for your spacecraft, if you can somehow dig stuff up on the surface of the object and use it for something, now you're cooking, because you land on the object, you're now able to study it, deploy rovers, and then maybe even turn its raw material into more rovers or more spacecraft. So there are some good reasons why you'd want to land on an interstellar object as it's making its way out into the universe. Hangman 747 Tin Man, what about just using the interstellar object as a shield? Yeah, I mean, if you want your spacecraft to survive, then there's a lot of good things that you can do with an interstellar object. Like, the reason why spacecraft generally die is because of cosmic rays. And so you're going to want to protect your spacecraft from cosmic rays. And the best way to do that is to dig under the ice. Once you get a meter under the ice, then you are protected from the cosmic rays. So if we wanted to put a spacecraft on an interstellar object and we wanted to survive for long periods of time and not get hit by lots of radiation, we would have it dig down under the surface on an interstellar object, find a cave and go into the cave, and then it would be safe from space radiation. So yeah, there's a bunch of good reasons. It's just we can't take advantage of the velocity of the object to take us places. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call that Q&A Plus. In this week's bonus question, are there multiple dark matters and dark energies? And I'll put a link in the show notes. All right, those are the questions that we had in this episode. Thank you, everyone, for asking your questions into the YouTube comments, everybody who joined me for the live show. As always, our live shows happen every Monday, but the time rotates. So you're going to have to check our channel for the listing for the next event. Now, I'm going to respond to 2 comments that on the same video that said the exact opposite thing. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bailout, Cooper Nelly, Darkfinger, David Gilton, David Matz, Evan.pro, Greg Feely, James Clark, Jerry Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Buck, Ryan Kaidu, Richard Williams, Sean Sargent, Stephen Farley-Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So we just released a video about sort of evaluating the plans for SpaceX to put AI data centers into space, and I knew it was going to be a controversial topic, and yet I feel like it's a thing that needs to be investigated, and so we did. And I had a conversation with somebody who has done the math and sort of thinks more about this kind of thing than me, and I thought it was very interesting. But it was interesting to sort of see the kinds of comments that we got. Like within the first few minutes, people were making conclusions about the video, and they hadn't even, like, maybe they're watching it at 10x speed. I don't know. But I also found that it's a really interesting litmus test for people because of this video, I had 2 people that were quite disappointed in my sort of overall perspective on artificial intelligence. On the one hand, someone said Fraser is one of the best science communicators on YouTube, but I do think his enthusiasm for AI is a bit of an Achilles heel on a topic like this. So I love AI too much. And then another comment said, you're making a blanket statement that AI taking off would be bad is the final unsubscribed straw for me. Keep yelling at clouds, old man. So I hate AI too much. And this was in the same video. And I've had sort of similar things happen with my perspective on SpaceX. And so generally, if I can get 2 people to complain about exactly the opposite thing in the same video, then I feel like I'm doing my job right, which is that I am trying to tackle a very complicated subject with nuance. That there are a whole bunch of things that, there are downsides that are happening to us because of AI right now that we can list off. And, Hank Green did a great video just a couple of days ago where I think he came up with 20 things that he was concerned about. Each one is like a little unsettling. Some of these things have already happened. Some of them are going to be happening shortly. Some of them may never happen. And yet if they did, they would be catastrophic. So that's the one hand. There are consequences. And on the other hand, people are seeing real change in their jobs. They're getting work done. They're being productive with this technology. And it's like not something you can easily just dismiss. And so we need to approach this topic very carefully and keep our eyes wide open and consider very carefully the path that we take as we move forward. You don't want to just accelerate wildly and just go YOLO and it doesn't matter, who cares? And you don't want to put your head in the sand and say all of the technology is dumb and stupid and anyone who thinks about it is an idiot and a grifter. None of this is going to be real because work is being done and people are using this. And so the right approach is to sort of think about the gray areas and approach it very cautiously and carefully. And that's the approach that I'm doing. And so, generally, if I get people on the same video, for example, who's saying, I'm unsubscribing because you love SpaceX too much, and on the same video, someone's saying, I'm unsubscribing because you hate SpaceX too much, perfect. Right? Then I am splitting the difference. I am tackling a complicated topic with nuance. And those who have trouble with that kind of nuanced perspective, they're not going to like it. And that's fine with me. All right, we'll see you next time.